neurology. So this is how the integrated healthcare in global populations are focused on. How as an engineer or how as a science fellow can contribute in shaping this healthcare community? That is the million-dollar question. So if we see any devices right now has a coded system, right? A chip, how to get signals or how to translate the signal into readable outputs. So with the semiconductor industry, most of the chips are started with the silicon, germanium, and second generation, third generation semiconducting materials like gallium arsenide, indium phosphide, tungsten, many other things, tungsten oxide, something like that. So in and around us, there are plenty of medical devices already in application, taking care of clinical abnormality, in providing solutions for rationalized therapy. So in such category, medical formulation, diagnostics, symptomatology, expected outcomes, and ideal treatment for a specific type of devices disease are the main focus of any chip technology, which largely you can imagine as on a fingertip small size. So how these chips are being made? Let us have a video on how it is just entered into our cell.
But making them is a long process comprising of great many steps. First, the silicon dioxide in the sand has to be converted into pure silicon. After that, it is cut into wafer-thin discs. In Dresden, these raw wafers are 300 millimeters in diameter and less than a millimeter thick. In our clean room, up to 35,000 chips are then made from each of these discs. In numerous process stages, the wafers are given their characteristic surface structure. After coating with a photoresist layer, the wafer surface is exposed, developed, and etched. This results in the desired conductor structure. Such structures are hundreds of times finer than a human hair. Dopants are then implanted in the material to increase the electrical connectivity of parts of the semiconductor. In subsequent phases, this and other process steps are repeated until the entire layout of the chip has been deposited on the wafer. This involves heating the wafer to more than 1100 degrees Celsius, in some cases up to 27 times. Up to 200 measurements are done, and up to 26 exposures. All in all, this can mean as many as 700 processing steps and 14 weeks processing time. Once this is completed, the microchip is assembled from as many as 30 such layers, like a mini skyscraper. Each layer has its own function. Interconnecting them makes the microchip highly complex. Semiconductor chips, the building blocks of our future.
So this is how all the chip technologies are transforming the healthcare community in addition to electronics or other appliances. So in this slide you can see integration levels in interprofessional practice. Nowadays it's an era of interdisciplinary, transdisciplinary and multidisciplinary. For example, I was a pharmacy graduate, landed in bio-nanotechnology and learned material science for constructing electrochemical biosensor. Right now, we are trying to build the electrochemical sensor platform for healthcare diagnostics, where I am often interacting with the engineers and medical doctors to learn about the problem in the medical sector, building that into prototype devices. Unless otherwise, if you speak with the other experts, you may not bring a complete product. The pandemic lesson, what we learned from the COVID situation, India is lack of sustainable or self-reliance technology. If you look at most of our expertise in our academic sectors or R&D sectors, they started with the BSc biochemistry, MSc biochemistry, PhD biochemistry, teaching biochemistry, and retiring with the biochemistry. Nowadays, people started learning about cross-disciplinary. Proper maybe they will be asked the question about the fundamental knowledge gap exists in the field. But that's not the case in abroad. Whether you are a civil engineer, whether you are a physiotherapy person, you are allowed to learn the other subject. You can have a translational projects once to provide some solutions. So there are many levels of interprofessional practice in the healthcare sectors. Whatever happening in the minimal collaboration, whatever happening in the minimal distance, whatever happening in the on-site collaboration, whatever happens at the distance integrations. If it is happened, for example, if you are allowed to take some imaging of organelles, someone before going into imaging, they may have to understand the metabolic parameters. You will be asked to take the blood profiling, you will be asked to take the heart functions before getting into any prescriptions. So that is how the level 4 or level 5 therapies are being done. If you are a cardiovascular person taking anti-diabetic and anti-platelet drugs, the dentist would be very feared of pulling your tooth, right? Why? Blood flow cannot be stopped immediately. So that some interdisciplinary or cross-disciplinary care is required. So if we have integrated healthcare system in abroad, since I was in Canada, for example, if we go for imaging, they will not produce the result. Instead, they will just share the data to the concerned thing, like telemedicine or translational things. So that kind of integrated practice was practically happening in the well-developed nation. Of course, in India also, some multi-specialty hospitals with advancement in their internal software solutions, they are providing such practices. So there are different levels of integrated practices there, which is actually feasible because of directly or indirectly because of the semiconducting technology. So I hope many of you are very familiar with drone technology. Tell me, that's helping not only in imaging or wedding photos or videography. It's also helping in the medical product and the equipment supply, hospital asset monitoring, remote patient care monitoring. In addition to that, telemedicines like visualizing the patients through webcam, providing medical care or medical training to the beginners. Sometimes one can actually perform robotic surgery from here to Pakistan or from here to somewhere else. Actually recently happened. Some medical, because of social intercontinental security issues, humanity basis, some medical solution has to be performed. If threat is there, intertransportation may be restricted. In such case, robotic surgeries are largely helpful in saving the life of anybody. So when we have advancements in integrated technology, we can have medical marketing based trade technology. That is how Zipline in US is making a huge profit. So Zipline is one company. They are very good in delivering all the medical related stuffs. Especially they helped in Uganda during the recent disaster.
More than a year ago now. We've been designing our next generation systems from the ground up, incorporating all that experience for that first operation. And so we redesigned pretty much everything about the plane and our ground systems to support scaled operations. So instead of being able to do 50 flights a day, we want to be able to do 500 flights a day from a single distribution center. We pull the blood, put a medical product in that order, put it in a package, put that package into a zip, and launch that zip. The aircraft weighs 20 kilograms, about 45 pounds. It has about a 10-foot wingspan, 3 meters, and it can carry about 3 pounds, 1.75 kilograms. The plane is measuring actively the wind speed and direction, and so if the wind's blowing in a bigger direction, it's going to compensate and drop that package so it lands on the ground about the size of 2 parking spots. it looks like kind of like a cake box with a paper parachute on top. A fixed-wing aircraft can fly dramatically farther than something like a quadcopter. And that's really important for what we do. It can fly faster, it can fly through heavier weather, and the approaches to things like safety are also much easier. On our aircraft, for example, we have multiple motors, right? The plane, if either one of those stops working, the plane flies just fine. We're in Rwanda today, and we're expanding to cover the other half of Rwanda as we speak, and next is Tanzania. From there, we are really focused on solving this problem, access medical products at a global scale. There's access medical product problems in the US and in the developing world, and we really want to solve all of those problems everywhere.
So to do that, actually you need 5 things. One is idea of conceptualization. You need mechanical expert. You need electronics and communication expert to bring such gadget. As rightly recently ma'am was discussing, maintaining the temperature of a product. Imagine blood samples. So reaching somewhere a different hemisphere, maintaining the temperature of medical products. It may be vaccine, it may be blood, or it may be any other products. Retaining the temperature of the maintaining the shelf life of any product is very important. So polymer chemistry, material science has to design the proper package. When you drop at the feet about 30 or 60, the shelf life or capacity of the material should retain the same. In such a way, the medical formulations for distance logistics has to be fabricated or formulated. So unless otherwise, if you don't discuss your needs with other disciplines and imagine the transdisciplinary idea, wonderful products may not ever come. So in this slide you can see the components of biosensors. Morning itself I mentioned about the basic biosensors of different components containing receptors. Unless otherwise we use enzymes, antibody nucleic acid or cells as bioreceptor, it is a simple sensor or biomolecular sensor. So we can use plenty of transducers that includes electrochemical, optical, thermal or piezoelectric. You can see since 1956 itself the race began related to diabetic monitoring. That's basically relies on oxygen measurement. Platinum electrode measuring the oxygen. That is the base for the conventional glucometer in the market right now. From the whole blood, glucose is detected with the enzymes modified on the electrode, which is called the glucose oxidase or glucose hydroxidase. That what we do, that will convert the glucose into gluconic acid and hydrogen peroxide. The byproduct hydrogen peroxide will reduce it to the electrode and generate the hydrogen, meaning it reduces the reaction. In few seconds we are just seeing in the number 120 milligram per deciliter or 200, 160 or 80 or 70 in the glucometer. All happens in less than few seconds or less than a minute. It's all because of the integrated combinations of communications between the circuits and the product. So the materials are the key here in oxidizing the target with the help of bioreceptors. That is the important area our expertise lies in. But you people can contribute the material science or basic electrochemistry bringing or prototyping those devices. You can see the glucose sensor now turned into immunosensor for making inflammatory sensors as well as various wearable products. In the morning slides also I mentioned about dental prosthetics, wearable contact lens like tattoo kind of sensors, wearable wristbands, neck bands, nipple kind of things, and diapers and other textile based wearable biosensors, where plenty of semiconducting materials are translated into the sensor platforms. So how sensors started? In a different way, I wanted to explain. Mother sends the feeling